Sustainable concrete using recycled e-waste. A project report submitted by Basit, Manish, Niranjan, Siddharth under the guidance of Mr. Manoj Kumar, Assistant Professor, Welltech High Tech. E-waste is one of the most growing environmental hazards. So as day by day the technology increases, the e-waste generation will also increase. So we have to find some method so that we can easily dispose this e-waste and make some good use of it. The aim of our project is to replace the sand, the fine aggregates, in the concrete with some amount of e-waste, partial replacement of e-waste. The objectives of our project is to provide a general awareness about the increasing threat of e-waste, to provide a solution for the formal recyclers in the way how they dispose the e-waste, and to find an alternative method for sand. So this is the literature referred from various national and international journals. So electronic waste. In short, we call electronic waste as e-waste. It is the general name given for any kind of discarded, surplus, obsolete, broken electrical and electronic equipment. And they are comprised of electronic devices and household appliances, which we see in day-to-day and everyday life. The e-waste which we are about to use in this kind project is printed circuit boards, PCBs. They are literally present in each and every electronic devices ranging from computers to televisions. And the main components of PCBs are epoxy resins, glass fibers. But we cannot incorporate PCBs directly into the concrete. We have to make sure that all the harmful components of PCBs like cadmium and beryllium are removed before we incorporate them in concrete. So this is the composition of PCBs. So in any kind of PCBs, this is the percentage distribution of silica, alumina, calcium oxide, and certain amounts of non-ferrous and recyclable materials. So what is the need for recycle of e-waste? We cannot, as I said before, we cannot directly use e-waste in the concrete because chemicals like beryllium, lead, cadmium, mercury, they are very hazardous and they can create a lot of health impacts. And one more interesting thing is that these chemicals are non-biodegradable, meaning even if we use in the concrete, it will pose some serious problems to the concrete we are using in future. So they have to be removed. The hazardous chemicals in e-waste can be removed only by a formal recycler. In our project, the e-waste which we have obtained is from formal recycler. Formal sector of e-waste in India. So formal sector, they are the sectors which are aided, funded by the government to carry out the recycling of e-waste in a legalized manner. That is by using all appropriate techniques and machines to shred, to grind all the e-waste in a desirable manner. So in our project, we sought e-waste from them. On the other hand, informal sectors they comprise of 90% of e-waste recycling in India. So there are very few number of formal recyclers and there are many informal sectors. The problem with informal sectors is that they have a lot of health issues and safety issues. Since recycling of e-waste involves dangerous, harmful chemicals, the workers who work there are prone to a lot of diseases and a lot of health hazards, and they are very labor intensive. And this even includes child labor, and there are a lot of legal issues in informal sector. So that's why we have not obtained e-waste from the informal sectors. So recycling process of printed circuit boards. There are 5 methods. One is manual separation, shredding, pulverization, density separation, and ball milling. In manual separation, by using hand manual labor, we separate the electronic waste from other components, plastic and metal components. Then they are shredded in a shredding machine. In this, the final output of the shredded particles ranges from about 3 by 3 mm. Pulverization, the main aim of pulverization is to bring about homogeneity in e-waste. In ball milling, what the main aim of ball milling is to activate a reaction between waste and CaO, calcium oxide, breaking down into organochlorine compounds. This is done by the collision between those balls inside the ball mill. Density separation is a very important phase. It is used to separate various kinds of metals and plastics. For example, magnetic separation is used to separate iron and nickel. Eddy current separation is used for cobalt, metal, and aluminium. Gravity separation is used for metal clusters, and to separate plastics from metals, we use electrostatic separation. So this is the final form of e-waste which we've obtained after removing all kinds of harmful and toxic materials. This is the e-waste which we are going to use in the concrete. So what is the difference between our project and the previous projects? In previous projects, what they used e-waste from informal sectors. But in our case, we use e-waste from formal sectors. The formal sectors are willing to give e-waste for free. So that's first plus. The second major advantage of our project is that in our project, we don't have any kind of harmful toxic substances. But in previous projects, since they've collected it from informal sectors, there will be toxic substances. And also the previous projects, the main aim was to replace coarse aggregates, gravel, with e-waste. But in our projects, we took a completely different take and we're trying to replace sand with e-waste. So as a result, what happens is, since we obtain e-waste from formal sectors, the cost is considerably reduced compared to other projects. So to begin the concrete preparation, any stage, the first important thing is preliminary test on materials. So as per this, the test for cement, first one is standard consistency test. The procedure is standard procedure over here, 33 to 35 mm depth of plunger, etc, etc. The setting time test. The setting time test is used to find the workability. It's a very integral phase to test the quality of cement. So this is preliminary test for aggregates, the sieve analysis test. So this is the test result of e-waste. The e-waste which we obtained was given to Chennai Metex Lab Private Limited, and by their lab results, it was found that our e-waste was completely free of any toxic and harmful substances. So our project can proceed. So this is the main proof that states that our e-waste which we use in our project is completely free from all kinds of harmful and toxic substances. So the sieve analysis were taken for various cases. The first case was used for river sand. The fineness modulus obtained from this is 2.9. The second case, the gradation was taken just for recycled e-waste, and the fineness modulus was about 2.06. The third case, we've combined the gradation. We took 80% of river sand and 20% of recycled e-waste. The reason why we took 20% of recycled e-waste is that 20% is the most maximum percentage of e-waste we're about to incorporate in the concrete. So if the sieve analysis for that percentage is taken, it's more than enough. And the combined gradation is about 2.77. And case 4, coarse aggregates, and the fineness modulus obtained was 2.13. The specific gravity tests were carried out, and as per IS 2386 part 3 of 1963, and the nominal specific gravity of fine aggregates used in concrete ranges from 2.4 to 2.6. The specific gravity is also determined from coarse aggregates separately for 20 mm and 12.5 mm. As per the observations from the tests, we found the specific gravity of river sand is 2.57. To be noted, it's zone 3. Of e-waste, it's 1.3. Combination is 2.39 and specific gravity of aggregate is 2.775. Water absorption test, it's the most common test for coarse aggregates. So observation is water absorption combination gives you about 0.8 percentage water absorption, and water absorption in aggregate is 0.48 percentage. The reason why 0.8 percentage, the reason why it's more in the combined is because e-waste absorbs an extra amount of water. The physical properties of fine aggregates and recycled e-waste. So this is a comparison to show that e-waste is really compatible with river sand. If e-waste has to be replaced in the concrete instead of sand, then it has to be ensured that the e-waste and sand have almost the same properties so that the project work can be carried out. So these are the various properties comparison in tabulated form. Crushing value test for coarse aggregates as per IS 2386. Crushing strength of aggregates, what we found is 23%. As per IS 2386, it is completely clearly stated that it should not exceed 45%. So our result of 23% is within the limit. Crushing strength of the aggregate is 16.5% in this case. And this is the most important part, the mixed design, manually worked out mixed design for M20 concrete. So the basic features, cement used OPC 53 grade, specific gravity of cement is 3.2, water cement ratio, the maximum level is 0.55, the range is between 0.45 to 55. Various steps. The first step is to find target strength. The second step, selection of water cement ratio. Step 3, selection of water content from table 2. So all these values which we've obtained in this mixed design is been referred from standard code books. Mix calculation. Finally, we arrive that the ratio required for M20 concrete is 1:1.7:2.88. We're going to use this mix in our concrete formation. So these are the visual representations which we carried out. So in this first picture, what you see is the mix between cement, sand, and e-waste. And in the second picture, as you can see, aggregates have been poured in. Mixing of aggregates and cube casting. This is skewing of concrete. After the casting of cubes, the most important test which comes now is compressive strength test. The compression test is the most commonly conducted test conducted on hardened concrete because it's a very easy test to perform and it's one of the most characteristic feature of concrete. In this project, we adopted replacement ratios of 5, 10, 15, 20 and a standard cube, that is a nominal mix without replacement. For each replacement ratio, that is for 5, 10, 15, 20, for each ratio, we casted 4 cubes. 2 cubes for 14 days curing and another 2 cubes for 28 days curing. So these are the details of compressive strength test. You can see the 0% replacement is nothing but standard cube without any kind of replacement. So this tabular column shows the 14 days curing of concrete, trial 1 and trial 2, and average. So from this tabular column, we can find that as the percentage replacement of concrete increases, the compressive strength, average compressive strength also increases. And this is for 28 days compressive strength. In this case also, we find that the average compressive strength increases as we increase the percentage of e-waste incorporation in the concrete. This is the comparison graph. The blue ones are 14 days curing and the 28 days are the brown ones. So we've plotted with percentage replacement on x-axis and compressive strength on y-axis. We can find a steady increase of compressive strength. Now next test which we carried out is flexural strength on concrete beams, prisms. So alternate approach is mentioned in clause 6.2.2 of IS 456-2000 that the flexural strength can also be calculated using the relation 0.7 into root FCK. So these are the prism casting. Test results. Even in this, we can find that as we increase the percentage of e-waste incorporation, the flexural strength also increases. The reason why we did not go above 20% is because above 20%, after referring a lot of journals, we found that beyond 20%, the concrete begins to lose its compressive strength. So our test results which we obtained are in a straight line graph, a gradual rise. So what's the conclusion, the inference? The inference is from this test result, the optimum point of replacement of e-waste is 20%. So what is the potential of this kind of project in future areas? Why should it be adopted? What is the use? How can it be implemented in different forms? The recycled e-waste, first thing, is free. So anything which you can obtain for free, and if you can use it in a good way, in incorporation in concrete mix, it's really desirable. And also second thing, the cost of the concrete production is very much reduced. And for now, this kind of concrete, e-waste concrete, they can be used only in manhole covers, concrete pavements, culverts, etc. For now, the implementation of this in structural members can be used, but it needs more acceptance from various kinds of construction institutions. The reduction of self-weight, that's also a major plus. The reason is because e-waste possesses the property of high volume and low weight. That is, bulk density of e-waste is low as compared to sand. So while replacing it instead of sand, the self-weight of the concrete is reduced to a considerable limit. So we conclude, the compressive strength of the concrete increases when e-waste is used for replacement of fine aggregates, but the optimum replacement is 20%. Beyond 20%, the concrete loses its strength and it begins to fault. The enforcing the recycling and handling should be only performed by the formal recycler only. It is very much recommended that we use e-waste which are generated by formal recyclers.